Welcome to the C++ parallel programming models talk. So a little bit about me before we start. At my day job, I'm building a relational distributed database at Regatta Data. This is a database internals field. If you, like me, are interested in infrastructure, low-level work, I think database internals is a fascinating field and I highly recommend it. Besides my day job, I'm also involved in C++ community activity. I'm one of the organizers of this conference. I also co-organize the Haifa C++ meetup group. And during COVID, when there was no face-to-face meetings, I started the Medabrim C++, Talking C++ WhatsApp group. If you're not part of any of these or some of these activities, you're welcome to join. Happy to see you there in Haifa and the WhatsApp group and obviously here. So why do we care about parallel programming? First reason is performance. Modern hardware has multiple cores or processors, and if we want to utilize all those cores, then we need to write parallel programs. The second is to hide I/O latencies. If you do a network call or a disk call, and it takes some time, you want to utilize the processor at the same time, you need to do something in parallel with that lengthy I/O operation, and to a lesser extent, responsiveness. If your program is facing a user and you're doing some processing, then you want to be able to still be responsive to other interactions with that user or other system. And this means doing things, again, in parallel. Why is it hard? Well, parallelism involves non-determinism. It involves data races and deadlocks. And when your programming model includes some structure, then it's much easier to do things right. So what a programming model gives us is a structure within our program. And this allows useful abstractions. Now, at compile time, when you code, this structure and these abstractions, they help us understand what exactly are we doing, what are our limitations, and avoid writing erroneous code. And from the library side or the framework side, it allows it to provide useful abstractions that helps us structure our code correctly. And during execution, having those abstractions and limitations allows the runtime to optimize the scheduling and obtain the optimal performance. Both of these ends are crucial in parallel programming. We want to be able to do things right when we write the code, and we want to be able to get the optimal performance when you execute the code because we care about performance. Now, if you're somewhat familiar with C++, which I assume you are, you've probably noticed that there's a wide variety of parallelism-related facilities and features. And from a distance, they might look like an arbitrary mix. And in fact, these aren't just random features that were selected without any planning. Those features are part of 4 different parallel programming models. And this is like the meat of the talk. So the first model is actually a non-model, but I had to put it in some bin. I call it the unstructured model. And that's the low-level building blocks that were provided mostly in C++ 11 and a little bit more afterwards. These are the threads, the mutexes, the atomics. It's not much of a model itself. It's more of a building block, but it gives us something. The next model is task parallelism, which is based on stood async, and it's a promise in future facilities. Then at C++20, we got coroutines, which allows us to get a cooperative multitasking programming model. And lastly, in C++17, we got the parallel algorithms, which provide data parallelism programming models. Now, these different models are not different abstractions. They're not built one on top of the other. I mean, some of them are built on top of the unstructured model, the unstructured facilities, but otherwise they are completely different program structure, and they don't mix very well. So in this talk, I'm going to overview the 4 different models: the unstructured one, the task-based one, the cooperating multitasking, and data parallelism. And then I'm going to talk a bit about mixing the models. The talk is a high-level talk, okay? I'm going to go into some details within each one of the models, but I'm not going to dive very deep. I'm not going to talk about the subtleties about the memory model or all the, the delicate complexities of coroutines. My goal is to make it easier to understand how those models look like and what are they used for, and when should we use each one of them. So, first model is the unstructured one. And in this model, it's what we get is the basic low-level facilities. It doesn't give us from the get-go any kind of programming model. If we want to use it, we have to adapt it to our own program. So we have some particular need that we want to implement in our code. We can go ahead and use those low-level facilities. It basically provides us with basic building blocks, okay? And they are the closest that we get to the hardware. And with that, we get the minimal overhead because we can use or make the most use of the underlying hardware. On the other hand, it's the riskiest model, it's the hardest to program, and it requires the maximal proficiency. The major components of this model are first the memory model, the low-level atomics and related facilities. The memory model is not a programming model. Okay, it models the underlying hardware, or at least the memory system of that hardware, and the ordering that our programming gets when it accesses the memory. Okay, so it's not a programming model; it's an underlying model. Above that, we get the threading and synchronization facilities, which is thread, the mutex, conditional variable from C++11, and more recently we got the semaphore and latch and berry in C++20. And then above that we have some convenience utilities that we can make do without, but we want to use the provided RAII wrappers and the stoppable thread and so on. So when do we want to use this unstructured model? When we want to construct higher level facilities, such as thread pools, and implement a spin lock, and if you want to create concurrent data structures, that's another exclusive use case. Ideally, or easier way to build concurrent data structures is using locks, but if you're living on the edge, you can make them lock-free or even weight-free, and you need those low-level facilities for that. And another exclusive use case is if you want to run some long-running services in the background. Okay, you launch a thread, you let it do its work throughout the program's execution. What's missing in this model is one thing is thread-safe shared state. Okay, we have multiple threads. They need to communicate with each other, and the way they communicate is either via some channels or with shared state, and that shared state has to be thread-safe. Okay, so we can use atomics, but for that we need to rely on the memory model, which isn't easy, and atomics are single pieces of information, so they're harder to make data sharing, more significant data sharing. We can use coarse grained locks, but that really hurts parallelism. So no concurrent data structures in the language for now. I saw that in C++26, we will hopefully get RCU, read copy update, which is a way to write concurrent trees or data structures, and hazard pointers, which is a way to manage memory in lock-free data structures. But that's to be determined. So the pros and cons of this model are, first, you get the maximal control. If you know what you're doing, you get good performance. And on the downside, you have to rely on the memory model, which is complex and hard to get right. And if you're not doing it right, then you get data races and deadlocks and non-determinism and all that fun. Now, taking a broader look, this model relies on threads. And a thread is an abstraction of a processor. Okay? So, like when you start to run your regular program, you have your main function, that's the entry point to your program. The same way, your thread has an entry point which it starts to execute. The thread itself has no functional semantics. It's an executor. Okay? What you run does have, but the thread is a general purpose facility. However, the code you have to run, or you want to run on that thread, does have to consider all the interaction with other threads. Okay? So on one hand, you have the thread, which is the executor, and it doesn't know what it's running. And on the other hand, you have your function that's running on that thread, and it has to take care about synchronization with other threads. So you have to interleave the synchronization and communication within your function. So that's like two different parts that don't mix well. If we had higher level abstractions and a clever runtime, then we can separate those two sides, and avoid your code from worrying about the synchronization. Let the underlying library or functionality care about all the synchronization and communication, and let your code do its thing without worrying about it. And that would give us less work, less bugs, and ideally better performance. And this brings us to the second model, which is a task-based one. A task is a limited piece of computation. It can typically be a function, or even in some cases a loop iteration or a lambda. It's characterized by having a limited amount of work, and ideally, and I'm talking now generally, not C++ yet, ideally it will have input and output, but no side effects. Okay? It doesn't modify any global or shared state directly. That's what you have the infrastructure for. And what tasks give us is a way to separate the functionality of the task, the functionality of the program, from the execution. So we can have one thread execute many tasks. We can have one task migrate from thread to thread. That depends on the actual model, but conceptually that's possible because we separate the functionality from the execution. Now, tasks are, by definition, asynchronous. If they're not, then you can just run functions. You don't need all this fuss. This means that the task is executed somewhere at some time. You can restrict or say when you need the outcome of the task, but ideally, you want to isolate yourself from the actual execution of the task. And let it execute until you actually need the results of that task. And the communication between the code that creates the task and the task itself is done by two abstractions. One is a future, which holds the outcome of the task, and the other one is a promise, which is the other end of the channel that your function pushes the outcome into. If you're familiar with C++ async, then you're familiar with those terms. They actually predate C++ by many years. They're from the 70s, if I remember correctly. I don't know how often those terms are used, but when we're talking about, in this context, they are relevant. So in C++, what we have, our major task mechanism is std_async, which is used to spawn new tasks. And it returns a future which you can use to get the outcome of this task. And the execution itself can be done on some thread that the runtime maintains. And this means that your runtime system, the C++ runtime, can actually create threads. It can manage a pool of threads. It can create them on demand. It can create them on the background. This is implementation defined. Okay, and to be honest, this is something that's a bit shaking. Can the runtime actually create threads that we didn't create explicitly? Well, yes, it can. So future and promise, as I mentioned, they are also part of the C++ async model. The future provides us a handle to the outcome of the task. And we can wait on that outcome when we need the task results to complete. On the other side, there's a push, and that gets the results from the task side. When we use async, we don't see the promise explicitly. Async hides it internally, but you can use those facilities in your code without using async. Now, another important thing in std_async is the execution policy. Okay, the first parameter is the when definition. It can be launched async, which means the task is going to run on a different thread than the one we are running on. It doesn't necessarily mean that we're running on a new thread. It doesn't mean we are launching a new thread. We might reuse an existing thread. This is up to the runtime, okay? But from our perspective, what we know is that someone else is running this task. Another policy is deferred. This means that the task will be executed if and when we want the result. We might not want it at all. In this case, it won't be executed. And the combination of async and deferred, which is the default, means that it's up to the runtime to decide when and where to run the task. So async has a few limitations. First of all, it's not composable. You can't say, I want to run this task, and when it ends, I want to have another task run, and create chains of tasks, which is kind of what I show like on the right side of the presentation, like a graph of tasks. So we don't get that. It was supposed to be part of the model, and there are some proposals about that in a TS that I guess never got merged into the language. We also don't have any execution configuration. We can't say we want to run it on one thread, on 100 threads, on a certain pool of threads. We don't have any scheduling options. We can't say, we can tell the model we want to pause a task and so on. And basically this model is pretty, I don't know, it's not heavily used, and it seems like it doesn't have a lot of future in the language. This brings us to the third model, which is cooperative multitasking. What we saw with the async model is that it's basically based on threads. And this means that if we run a task and that task is blocked on some I/O operation, on some lock, then it basically blocks the CPU, okay? The operating system can switch and run another thread, but it's not on our control. Now, if we have way more tasks than CPUs, then we want to be able to run something else. If one task is blocked, we want to be able to run another task. If that's not the case, by the way, we have more CPUs than tasks, then we don't care. But if we do, then we want to optimally use the processors that we have and want to be able to control that. Now, the tasks are something we define. The operating system, which schedules threads, isn't aware of tasks. So if we have one task that is stuck, then the operating system can't help us. It can't schedule another task. It can schedule another thread, but not another task. So that's not optimal use of our CPUs. There are ways to break down task execution by having tasks that get stuck, get paused, and then run a callback for their continuation. If you come across this programming model, you probably know that it's pretty inconvenient and pretty complicated, and that's not the easiest thing to do. So we want an easier programming model. And that we get with coroutines. So a coroutine, which was a feature introduced in C++20, is basically a function that can be suspended and resumed. And it can be done so it can be suspended by the coroutine, the function itself, and it can be resumed from the outside. But this is all done from our code. There's no operating system involvement here. You don't have to write any hacky assembly, which was the case before we had coroutines. We have full language support, it's fully defined behavior in case of errors, and so on. So let's look, and this is a very superficial description about how coroutines work, but I'm talking about a model here, so bear with me. We define a coroutine that does something. It first prints before await, then it suspends itself by calling co-await suspend always. The suspend always is something I don't have to get into the details, but I'll discuss co-await in a minute. And after this suspension, when it gets resumed, it calls the after await, or prints the after await. And then on our main function, we invoke that coroutine, basically a function call that starts its execution. When that coroutine is suspended, we print suspended, and then we resume the coroutine. So the control flow in this case is as follows. We first launch the coroutine, then we print before await, then the await sends us back into the caller. We print the suspended output, And then we call the resume, which brings us back into the coroutine. We print whatever we print, and then at the end of the coroutine, we return back to main. So this is the flow of the control. Now, the major component in coroutines and the way we use it is the co-await keyword. And co-await gets an expression which is evaluated to an awaitable function or object, which means it's an object or a type that has 3 functions: await ready, await suspend, and await resume. And they are actually the machinery that handles the suspension and the scheduling of the coroutine. So when we call co-await foo, what happens is we first execute foo, and then we get some result back from foo, which is an awaitable, something we can query and see if we need to suspend. And if that awaitable determines that we have to suspend, then the coroutine can return or switch to some other context. Okay? So co-await can either suspend the coroutine and return to the caller, which is what I've shown on the first example, or it can switch to another coroutine immediately. The co-await does not create any parallelism, okay? And this is important. It's not like async that spawns another thread or anything. It just switches the context of the execution to some other context. And this means that once you switch the context, then it's up to your program to track the suspended coroutines, okay? And it's up to your program to determine when you can resume a coroutine and have it actually resumed. This isn't managed by some runtime, not one that exists in the language. So to make coroutines useful in this task-based model, there are other uses of coroutines, which is generators, which I'm not going to talk about. So if you want to use coroutines within a parallel execution context, then you have to have some source of parallelism. And that can be async I/O disk or network, or you can have worker threads that will execute multiple coroutines and move executions from one another to the other. And you want to have a scheduler that is aware of coroutines that are executed, that are suspended, and dependencies between the coroutines. Okay? And this is something you don't get for now. So let's take a look at what would a coroutine-based multitasking execution look like. So we have a scheduler that starts some coroutine. And that coroutine is a task, okay? And it invokes some async I/O. You start a disk read, and then you can continue. At some point, you'll be notified that read is completed. Now, the coroutine, knows that this is an async disk read, so it knows it doesn't have the result yet, so it suspends itself and lets someone else execute instead of just waiting. And once it's suspended, the scheduler is aware of that. And the scheduler can then take another coroutine that was either suspended or hasn't started yet and start to execute it on the same thread. Once the async disk read you started completes, then the scheduler has to be notified in some way. This again is part of the runtime that you don't get in C++, but you can build yourself. And when it gets that notification, it marks internally. It can mark the suspended coroutine as ready for re-execution, and at some point when the scheduler determines it has it can execute that for suspended coroutine that is now ready to be continued, then it can resume it. Okay? So we have a coroutine that executes from its point of view. It executes sequentially. The code is a single function from start to end, but it was actually suspended while it was waiting for the disk read to complete. And when it resumes, it has all the data it needs. Now, concurrency and parallelism are two terms that can be confusing. And the same goes to the way we, they're equivalent terms in Hebrew. So concurrency is b'makbil, and parallelism is bo-zmanit. Okay? Let's demonstrate that. When you have concurrency but no parallelism, it's like you getting two tickets in Jira. You have two bugs. You start to work on both of them, but since there's only one of you, you have like two tickets in progress, but you're not working on both of them at the same time. You can switch between them, but there's only one of you. So it's basically like you're running them sequentially. When you get multi-CPU parallelism, then your friend comes and takes one of the bugs. So now two of you are working on two different bugs. Two CPUs working on two different tasks. So you get concurrency, which means two contexts being executed at the same time, or two contexts are in flight, and they're actually being executed at the same time. So this is parallelism that is based on having multiple CPUs. And another option is having parallelism that is based on I/O and CPU parallelism. In this example, this is like getting two bugs, sending one of the bugs back to the QA department and asking them to reproduce it. And while they are working on the reproduction, you go ahead and work on your other bug. Okay? So the QA department is, in this case, like the disk. It is a parallel execution resource. It's just not your friend that's working on the bug. So if we want to do parallel coroutine execution, then ideally you'll have one thread per core. No need to have more than that. And suspended tasks can move between cores. Once your task is suspended, you might want to have more, like, you might want to have it prefer to run on the same thread, but it's not necessarily. And the fact that it can migrate from thread to thread is transparent to the task itself. But if you use within your task facilities like thread local, then you're getting into trouble because your code is actually migrating and you're not going to get the same thread local variables. If you want to use synchronization primitives, locks, in a coroutine context, okay? Your coroutine is running and then you want to lock something. Then if you're using the thread synchronization mechanisms like mutex, then you're actually blocking the whole thread, okay? You have a coroutine, it hits a mutex, and then it blocks. And this is not what this model aims for. When you block, you keep the thread idle, and you're not utilizing the CPU. What you do want to do in this case is use synchronization primitives that are coroutine aware or tailored for a coroutine execution, which means when you try to lock, then you actually get a context switch in the coroutine scheduler, okay? And again, this is not something that we have in the language. This is something you have to implement if you want to use this kind of model. But what this means is that the locking is actually just allowing another coroutine to execute as determined by the scheduler. Now, all this means that since we don't have this kind of scheduler, if you do want to implement it, you get all the headaches of writing delicate parallel component. The scheduler has to have multiple threads. It has to make sure that it properly maintains its internal data structures. This is an easy task. You're basically just moving the complexity from your task or your functionality that is based on your program's business logic to a dedicated component that manages that complexity. And once you get it right, then whoever writes tasks doesn't have to deal with all that concurrency and parallelism complexity. So I've been talking about threads and I've been talking about tasks. A quick recap. We have kind of different use cases for each one of them. So in the case of threads, a thread is an abstraction of a parallelism. Parallelism itself, it's an abstraction of the CPU itself, while a task is a piece of functionality. It isn't aware of the execution context. It just breaks down your program's functionality. Threads are more suitable for long-running operations, services, workers, etc., because they are expensive to execute or to create, and you don't want to create threads in a rapid pace. Tasks, on the other hand, are supposed to be fairly short and independent, so you can create many of them. Threads are suitable for long and complex parallel operations. If you have some long-running computation that you want to parallelize, then threads are a good choice. On the other hand, tasks are more suitable for local operations. You want to run do some disk read or so on and so on. And if your program includes many threads and you split the work between them, then you want to make sure that each thread gets the same amount of work, so you get proper load balancing and you fully utilize your resources to the end. And tasks, on the other hand, since they are shorter and more dynamic, then you get more dynamic load balancing and you don't have to worry so much about it up front. Another concept which is related, so I'll mention it, but it's not actually part of this model, is something called fiber or user threads or green threads in some context. And those are actually stackful coroutines. So the coroutines that we get in C++ are stackless. This means that when you create a coroutine, you get allocated like a stack frame on the heap, and that stack frame holds the state of that particular function, that coroutine. But it doesn't hold, if you call like one coroutine creates a chain of functions, then those functions are placed on your main thread's stack. And this has many limitations. On the other hand, in the case of fibers, each coroutine has its own stack. And this means that you can start a fiber, you can make recursive or many calls, and suspend that fiber at any point you want, and it will keep its own stack, and it can resume from that stack, and it will all go fine. Now, fiber, one like fundamental difference between fibers and coroutines is that a fiber is actually an execution context. It's an executor. Okay, it's more similar to a thread in that it can get start point of an execution and go ahead and execute with occasionally being suspended and resumed, but it's not limited to a small part of functionality. You can have like fiber pools and long-running fibers, and that's fine. It's an execution context, like a long-running execution context, as opposed to coroutines, which are basically a single function that is more limited in scope. Fibers require an ecosystem. Okay, as I mentioned before, in the case of coroutines, that if you want to suspend if you want to synchronize coroutines using locks, then you need dedicated locks. Same goes to fibers. You need to have a dedicated scheduler, and you need to have dedicated synchronization object because you don't want to block the whole thread when you block a certain fiber. Fibers aren't supported in C++. There are some efforts to add preliminary support. I have no idea if and when this will be added to the language. So this brings us to the final model, which is data parallelism. And in this model, the parallelism stems from the data itself, okay? And in this case, we assume we have a lot of data, and the data can be broken into separate or small, mostly non-dependent pieces of computation, okay? So we can basically get a large collection of data, a large amount of data, and break it into parts and execute each one of them in parallel, okay? It's actually it's kind of a way to accelerate large computations over a large amount of data. This model exists in the C++ 17 parallel algorithms. Okay, you have an algorithm, a standard algorithm. You can define an execution policy, and you give it a container or iterators, and you get that the parallel execution. So when you invoke that algorithm, you start with a sequential execution context, okay? And then you define the execution policy, which is a declarative API, okay? You say what you want or what are the limitations that you require, and the runtime can make use of that. And then the runtime can execute your algorithm in parallel or maybe sequentially if that's more appropriate. It has its own discretion. So this model is a true high-level abstraction, okay? You have some ways to customize the behavior. You don't have any control over the actual parallelism except what you say in the execution policy. You can say you want to run it on 2 threads or 100 threads over one core on the other. You can control that. You have no control about the scheduling of the internal operations and how they are distributed among all the cores that execute them. And the fact that you don't have that control means that the runtime has it. Okay, so this gives the runtime a lot of control and a lot of power, and it can be very efficient. And if you use this model properly, you can always misuse a model. Then you get no data races, and you get no deadlocks, and you ideally get very good performance. So to use a parallel algorithm, what you basically need to do is to define an execution policy, okay? Which is the first parameter that this reduce function here gets. And this is the biggest difference between like regular sequential algorithms and parallel algorithms. The other minor difference is the iterators are different in the parallel algorithm case. We don't have to get into that now. The complexity requirements of parallel algorithm are slightly more relaxed. You know that in general, algorithms have those. They have their some complexity constraints, but in case of parallel algorithms, when you parallelize something, you might have to do more work than the sequential operations. But since you're doing it in parallel, it pays. Okay, so you're doing a bit more work, but overall it runs faster. And since this is an abstraction, you don't have actual control about where the thing is running, the algorithm is running. In theory, it can execute on other execution contexts, not on your CPU, but on a GPU and so on. So let's go over the sequential policies, the execution policies. The first one is sequence, which means your execution should just run on the current thread that it's running on, no parallelism, okay? This is almost as if you're running it using the regular sequential algorithm, the old style, with minor differences, what happens if you have an exception and the iterators, but otherwise it's the same, okay? Now, note that the parameter that the algorithm gets, in this case the execution seq, is actually an object. It's not a type or an enum. It's an instance. The seq is an instance of a type called sequence policy. It's a standard object. There's one instance of it. And the reason that this is done this way is because this allows the algorithms to be overloaded by the policy, okay? So the decision which execution policy you want to pick is a compile time decision. This is not something you decide at runtime. The second policy is parallel policy, and this means that the execution can be broken over multiple threads. Per thread, the semantics is as if it was running on a single one, a single algorithm. Okay, so one of the parallel algorithm threads picks or starts to process a certain piece of data. It will process it from start to end. Okay, it won't stop in the middle. It won't switch to other parts of the container. So now, if you add some lambda that's going to be executed in the data during the algorithm, and that lambda accesses some shared state, then you can definitely get into data races, and this is certainly something you want to avoid. Okay, but it's possible. The third policy is called parallel unsequenced policy, and it differs from the previous one in that now execution doesn't have to run, or a single thread doesn't have to complete the current object that it's working on from start to end before it moves to the other one. It can interleave processing of multiple data items, okay? And this adds a bit more restrictions. The good thing about it is that the fact that it can process multiple data items in parallel or at the same time in an interleaved fashion makes it possible to use vectorization, mostly SIMD instructions. Some of you may have attended my lightning talk yesterday. I discussed this a bit. So this allows not only multi-processing, but also within a certain not multi-threading, but also within a single thread, we can use dedicated parallel instructions, the SIMD instructions. The last policy is unsequenced policy, which means you're still running the algorithm in a single thread, but now it can, again, use vectorized SIMD instructions, okay? So we're not creating any additional parallelism, but you're getting some acceleration. In addition, the standard allows vendor-specific policies. So some vendor can add execution policies that will make your parallel algorithms run on other kind of hardwares, not on just the CPU, but also on a GPU, on an FPGA, async, or whatever. Now, it's worth noting that parallel algorithms doesn't mean parallel containers or thread-safe containers. You're still bound to if you're using the standard containers, then you're still using the thread-unsafe ones, okay? This means that if you're writing, your parallel algorithm is writing to different elements of a vector, then that's safe because they are different memory locations. But if you're trying to insert into some tree-based or pointer-based data structure, then you'll cause races because you're trying to modify the structure of that container, and standard containers are not thread safe. You can't modify their structure this way. So you want to avoid that, okay? So the last thing I want to talk about is mixing models. So for starters, if your program is mostly using the unstructured facilities, the low-level threads and mutexes and so on, for instance, you're implementing your own server that's running multiple threads to handle user requests and so on, and you're utilizing most of the machine's core as it is, okay? Then you can certainly use coroutines for async I/O. And you don't really have any additional resources for other models such as async or parallel algorithms, okay? If you have 8 cores and they are all busy running threads that you've created, then there's no point in creating or using parallel algorithms because you have no cores for those parallel algorithms. On the other hand, if you're using just a small part of those cores that you have, for instance, your parallelism is only manifested in some background services, then sure you can use tasks or one of the task models or parallel algorithms. The impact really depends on the implementation, okay? The parallel algorithms runtime doesn't know what threads, or it doesn't necessarily know if you're running any threads, okay? So it might just say, I see the machine has 8 cores, I'll just parallelize over all those 8 cores, but you're already busy with running 2 threads, then some of the parallel algorithm threads will be able to execute while the others will be stalled. So you have to take that into consideration, and you also have to worry about shared state, okay? If you're running, say, parallel algorithms about some container, and one of your own threads is also modifying or accessing those containers, then you'll get a data race. The second situation is that you're using async heavily, which means that most of your cores are busy running async work. In this scenario, there is really no point in launching new threads, especially not from an async context. That just doesn't make much sense. And using coroutines in this case also doesn't really make sense. If you're heavily relying on the async thread-based execution model, then there's just no point in using async I/O. You can just use blocking I/O and let the kernel do the scheduling. On the other hand, if you're using async very lightly for, say, UI workers or so on, then you can certainly use parallel algorithms from within an AC context. And you can you don't want to use threads. You using synchronization mechanisms from the threading model also doesn't really make sense. A next option is using a coroutine-based model. In this case, if your scheduler is using all of the available cores, then there's no gain from using the other models, running new threads or parallel algorithms. And if you're using just a few cores for your coroutines, then running parallel algorithms from within a coroutine will block that coroutine, which is against the way we want to use coroutines. Using async makes some sense because it's async. So this might work, but otherwise it doesn't really fit. And if you're running parallel algorithms most of the time, accelerating some large data computation, there's no really point in using any other one of the models from within the parallel algorithm, like the extensions that you have there, the lambdas or the functors that you give it. So to summarize, we have 4 different models. First is the unstructured one, which is the lowest level building blocks, which we mostly got at C++11. The second is the task-based model, which is based on std async, which means you functionally decompose your program and use async to execute the different parts. This is a pretty incomplete feature and barely used. The third model is the newest, which is the cooperative multitasking that is based on C++20 coroutines. It is a great facility for doing async I/O or handling async I/O. It does miss a scheduler, so if that's something you want to use, you have to do it yourself. And the last model is data parallelism, which is basically a way to execute computation over large collections of data. And this is like the most complete model in the sense that it's a declarative API, and you have a complete runtime that makes sure that schedules the execution and controls it. And the last point is mixing models is hard, and so is parallel programming in general, which is why we want to use some modeling or some structure. With that, I'm done. I'm happy to take any questions within a minute and a half we have. Yeah.
Since some of the aspects is managed by the runtime, can this solution be viable for hard real-time systems?
I don't think it makes sense. I mean, it's too risky. Coroutines are the closest, but in this case, the question was, is this suitable? Is any of those models suitable for hard real-time context? So since in coroutines you bring your own scheduler, then you can make sure that it's the most lightweight and you have the most control, but then it's up to you, okay? And coroutines do allocate. The other models are out of our control, so they won't suit. Yeah.
So from what I understand, the coroutines are themselves like a building block at the moment. Are there any plans to actually standard something higher level that uses it?
Yeah, so the question is, coroutines are basic building blocks, whether there is a plan to provide higher level facilities that will make using them easier. Yesterday, Robert Leahy gave a talk about senders and receivers, which is a way to utilize coroutines in a more structured way when dealing with async operations. So that's something that definitely fits them all. And that will also provide some scheduling facilities. There's also an effort to do executors that might fit into that. But what I described here, I'm not aware of that. I'm not a member of the ISO committee, so I can't say much more than that. We have like a minute, I'm overflowing. I'll take more questions offline because we're out of time, but you have a long break now, so I hope you're happy with that.